Okay, thanks. Hey, morning. Let's start the lecture, and so we'll finish the free vibration part. Then we'll get on to the solution for second-order non-homogeneous ODE. Okay, yeah. So free vibration, basically, we talk about two different free vibration. One is the free vibration without damping, and the other one is free vibration with damping. So we started this one in the last lecture. This is a free vibration with damping. So M, B, K, they're all physical quantity. They're all greater than 0. And we know that the solution for this one here is negative B plus minus B squared minus 4mk over 2m, right? So instead of using M, B, K, we define a new set of parameter. So we define our natural frequency as K over M, okay? And then we define our so-called damping ratio zeta, okay, which is B over 2 root Km. Okay. Now with these two new parameter, the original second-order differential equation can be written as x double prime plus 2 zeta omega n x prime plus omega n squared x equal to 0. Okay, so this is a new second-order differential, not a new one, but it's just a different way of writing it using the new set of parameter. Then the solution for this one here is lambda 1, 2, which is negative, okay, zeta omega n plus minus, okay, omega n root zeta square minus 1. Okay, so now we look at the roots of these two right here, and we talk about the three different cases, okay, and we look at the three different kind of basically vibrations, okay. So the first case we talk about is, okay, when zeta squared is greater than 1, okay, which basically when zeta is greater than 1. When zeta is greater than 1, that's equivalent to say B squared is greater than 4mk at here, right? Yeah. And this case here we call it overdamped system. Okay. So why is it called overdamped system? It's because when zeta is greater than 1, both lambda 1 and the lambda 2 are less than 0. Okay, both of them are less than 0. So if both of them are less than 0, the general solution is y equal to negative lambda 1t c1 here, c2 lambda 2t. So you can see now the general solution contains two exponential functions, exponential decay functions, right? Sorry, no, not lambda negative, just lambda, right? They contain two negative numbers here, so two negative exponential decay function. So there's no oscillation, right? No oscillation. So this is why it's called overdamped. So the damping is too much. You know, there's too much damping there. You have an initial position, you have an initial velocity, and you let it go, right? Then what happens is, so this is a spring, you let it go, it's gonna just basically slowly and back off and until it settles down at the initial position, at the equilibrium position. All right? Yeah. Just like a door over there, you know, you close the door or open the door, so there's no oscillation. So it just close. It'll basically close itself slowly. Okay. So the second case, okay, is when zeta equal to 1. Okay, so this guy equal to 1. If this is equal to 1, essentially this term is gone and you have only one term in here, right? And that gives you the second case, which is what we see that you have a repeated roots. Okay. For this particular case, when zeta equal to 1, so what we have here is b equal to this term here, right? So zeta equal to 1, b equal to this. And that b equal to this, if you recall that, we also had a definition called the critical damping ratio. So when b equal to root this guy here, this is called critical damping ratio, okay? Yeah, critical. So in this particular case, what we call is a it's called critically damped system. Okay, critically damped system. So why is it critically damped system? So critical basically, this is a boundary. Okay, this is a boundary here. As you can imagine is, here zeta greater than 1, no oscillation, right? Here zeta equal to 1. Then what happens when zeta is less than 1, right? So there's three different cases. So that's the boundary here. When your zeta is greater than 1, no oscillation. When it's less than 1, you would have oscillation. So when zeta is equal to 1, it's just there, right? You don't see the oscillation yet, but just a little bit change in the zeta, it changed the condition. Okay, so that's why it's called critically damped system. Okay, so for this particular case, we know our solution at not y, right? We use x here, so we use x of t here. For this particular case, our solution is C1 e lambda 1t, okay, plus C2t e lambda 1t. So there's only one lambda, right? And lambda here is negative zeta omega n. So lambda is a value less than 0. Then the first term is exponential decay function. And the second term, it's a t. As t goes to infinite, I think I proved this one here. As t goes to infinite, this t goes to infinite. And this e lambda 1t goes to 0. So whether this term goes to 0 or not, you have to check the limits, right? I think we used the L'Hopital rule to check the limits. So that turned out to this t, okay, this guy also goes back to 0, okay, if you use a L'Hopital rule. As t goes to infinite, and this term actually also goes to 0. So here's the first term is exponential decay. The second term is also exponential decay, basically. So now you can see there's still no oscillation, right? There's no sine, cosine here getting involved here. So if I have a, for example, if I have an initial condition at here, let's say maybe I have initial condition 0 equal to 3, and initial velocity, let's say just a 0, right? Yeah. Then the typical response based on this initial condition, maybe it's just going to be like this, okay? Still like this. So still no oscillation, right? But if for the first case, right, with the same initial condition, so let's say this is if this is a case 2, if this is case 2 here, okay, then for case number 1, for the case number 1 overdamp compared to this one, what do you think? It's going to be looking like this one here, okay? It's going to be like this. Why is that? Because overdamp, so there's more damping. Basically, the response will be slower, right? It will be slower because you get damping in your system, okay? So that's what this first one will look like. Okay? Yeah. So that's the second case here. So third case, okay, is when zeta is less than 1. So now you should see oscillation now. So when zeta equal less than 1 here, so what's my lambda? Lambda here is negative value here, right? This value is negative. Then you have a complex number basically. Now you got a complex number showing up here now, right? So your lambda, okay, so in this particular case, what we call it is under damped system, or you have underdamped response. Okay, so your lambda will be plus minus j omega n root 1 minus this. Okay, your lambda will be this. So you got two complex roots. When you got two complex conjugate roots, And as we learned about the general solution of a second order homogeneous ODE, we would expect to have sine, cosine to show up, right? And that's where we see our oscillations, basically. Okay. So this is our alpha, and this is our beta. Then our general solution is E alpha t, okay, and then A cosine beta t plus B sine beta t. Okay, right. So now you can see I got oscillations here now, right, because of the sine and cosine term. Okay. Now at the same time, you also have this e to the power of alpha t. Alpha is this quantity, and this is a negative quantity because zeta omega n are greater than 0. If this is a negative quantity, this is an exponential decay quantity, right? So you have exponential decay curve multiplied with a constantly oscillation. So which basically, I think I draw something like this, which basically give you certain kind of a response. Oops, what's going on? So which basically give you kind of response. Let's say I'm still going to use x0 equals 3x prime equals 0, this unconditional condition here. This is 3 here, right? Yeah. What did I touch? So you will see something like this. Okay, something like this. Okay. And the boundary, the boundary of this oscillation. Okay, the boundary. Okay, the boundary here is the E alpha t. Okay, E alpha t. Is that good? Okay, so come again? Why is it underdamped? Yeah. Okay. First of all, this less than 1 meaning this term is the negative, right? If this is negative here, then I have basically a complex number. So which is why I write my lambda 1 and 2, okay, by taking a j out, and instead of writing z squared minus 1, we write z 1 minus z squared. So this is greater than 0 now, right? Okay. So this is a complex number. When you have a complex conjugate roots for a second order homogeneous ODE, and this is alpha defined as beta, then your general solution is this. Okay? And for this particular one, if you recall that, we can rewrite this one as this. Okay? So we can rewrite this quantity as this one here. So what's inside the bracket here is an addition of a sine and cosine, but actually it's basically it's a sinusoidal in the end. Okay? The sinusoidal signal in the end. The amplitude of this sinusoidal is this one here. Okay, it's this. Is that good? Yeah. So I think more precisely, I would say the bonds that are here is actually multiplied by this guy here. Okay, and bottom here it's negative. Of this. Okay. So you see, you have a response which has amplitude here. Multiplied by this cosine term, right? Cosine term. So if I don't have these bonds here, just cosine term, that's constant oscillation, right? However, now you have a amplitude term, but the amplitude is not a constant amplitude. Amplitude is modulated by this E alpha t, and E alpha t is a exponential decay curve. So that's why you have these oscillations here, right? So why is it underdamped? Because you have oscillation now. So basically, whenever you have a system showing oscillation, that's an underdamped system. Okay, yeah. If you have system doesn't show oscillation here, that's overdamped system or critical damped system. Okay, yeah. So here's basically the 3 different cases. Okay, and truly there's nothing new at here. Even though you see so many different symbols, right? There's actually nothing new. It's basically relates the general solutions of a second order homogeneous ODE to actual mechanical systems. Okay, what I want you to do is to take a look at some examples. Well, we wouldn't call it examples here. Basically, some kind of combinations. So look at some kind of combinations of MBK. So combinations MBK. The reason is what you want to see is what combination MBK would give us this underdamped, overdamped, or critical damped system response. Okay, so that's the effect of this examples in the lecture, page 7. So there's nothing new there. Just take a look at them. Okay, and if you've got time, try to plot the response using the code that I gave it to you in the lecture notes. Plot it using Maple, or you can also plot it using MATLAB. Either way is fine, right? Yeah. To get some sense of system response based on certain set of physical system parameters. Okay. Yeah. So one of the assignments, the bonus question is ask you to plot these things using the templates, the code that gave it to you guys. Okay. Any questions? Okay. Yeah. Okay. So now let's get on to new topic here, which is solution of second order non-homogeneous ODE. Okay, second order non-homogeneous ODE. So non-homogeneous basically means you, instead of having no input, now you have input into the system now, right? Okay. So let's lay down a general format for second order one here. There we go. So this is the second order non-homogeneous ODE. ABC could be constant, could be time varying parameters, right? Yeah, just in case. Okay, so when you look at this one here, first thing is I need to give you a theory, because our objective is to find the general solution of this one, right? General solution. So here is one of the general theorem here, okay? In terms of the general solution. Okay, so let's say what the theorem says is basically if y, I would call YH, okay? If YH, okay, is the general solution to AY double prime plus BY prime plus CY equal to 0. Okay. So what does this mean? So this basically the YH is general solution to which one? To the homogeneous one, right? To homogeneous. And if YP is particular solution, okay, is a particular solution to AY double prime plus BY prime plus CY equal to F of T. Okay. So there are two things got involved here. Okay, so one is suppose that we have a general solution to the homogeneous one, and also that suppose we have a particular solution to what we're looking to the equation where we're looking for, right? Okay, then the general solution to our non-homogeneous ODE. Then general solution, okay, to let's call this equation 1. Okay, to the equation 1 is y equal to YH plus YP. So that's the theory in terms of the general solution here. Okay. Yeah. If I know YH, maybe YH is C1Y1 plus C2Y2, right? And then basically, then you plus this particular solution YP. So that's going to give us the general solution to this non-homogeneous ODE. Okay. Is that good? Yeah. So the first line of this one here, okay, this apply to high order. Basically, if you have third order, fourth order, you can still use this theorem here. Okay. This second one here only applies to second order, right? Because I only have y1, y2 here. Okay. Yeah. Is that clear? I think I'm going to skip the proof here, which is in my lecture notes, all right? But I think it's pretty easy proof if you look at the lecture notes. Okay. Okay. The YH at here, okay. Sometimes we also call it complementary, okay, solution. Okay, so in some textbook, instead of using y, they write YH. So in some textbook, they write YC. Okay, so they're the same thing, all right? Yeah. And YP is called particular, right? It's particular. So now you look at this general solution in here. If I wanted to find a general solution, actually I already solved this general solution 50%, right? Because we know how to solve this. We know how to obtain this YH. YH is the general solution for the homogeneous one. So that 3 different cases, you know, right? You get the characteristic equation. Okay. So the only problem here is how do we obtain a particular solution YP? So that's the only challenge at here now, right? Okay. So the whole objective here is we want to obtain an YP at here. Okay, so in order to obtain this YP at here, okay, so we're gonna look at different cases at here. Okay, yeah. First we're gonna look at AB when ABC. So when A, B, C, basically the coefficient of this one here are all constants. Okay, so that's a simple case, you know. So when they are all constants here. Now, when you have when they're all constant here, so the method that we're going to use is so-called, okay. So we're going to use a so-called method of undetermined. So undetermined coefficient. Okay, undetermined coefficients. If this name is too hard to remember, and there's another name, I call it lucky guess method. Yeah, so it's a lucky guess, but it's not that actually. Yeah, you're not random guess. It's a guess based on certain rule, right? Yeah. Now, when ABC, okay, when ABC are not constants. Okay, then what we can do is we can use a so-called variation of parameters. So this name sounds familiar, isn't it? Right? I think I used this name in the proof in the procedure of finding general solution of the second when you have a repeated double roots, right? Yeah. So when they're not constant, you can use this method here. As a matter of fact, this one here can also be used, okay, to the first case. Okay, so if they're all constant, you can still use variation parameters here. But usually, this involves a little more calculation, but which is more suitable for the second case set here. Okay, yeah. So let's look at this case number A at here when A, B, C are all constants. Okay. Yeah. So this is where the handout to you guys come into the hand. Okay, you're gonna take a look at the handouts there. All right, let's lay down this second order here. Okay. So the key idea is this. Okay, the key idea. The key idea is you want to find a YP, right? So we found a YP, okay, based on f of t, okay, based on f of t. So in the lay words, essentially we take an initial guess. So we take an initial guess of YP, okay, based on what f of t look like. Okay, based on what f of t looks like. So this is actually makes a lot of sense. Basically, see, here we have the linear system, right? It's the linear system. One of the feature of the linear system is whatever you put it into the linear system, you know the signal that you put into the linear system. Okay, for example, you're putting a sine or you're putting exponential, right? And the linear system usually will try to preserve what this input looks like. So the output here is y at here, right? You're looking for a particular solution satisfy this one here. Basically, you're looking for a response. So our objective, our idea is if the output looks like f of t, so we take our initial guess. We guess that our f of t, or make our f of t. We make our yp of t to be something very much look like the input f of t. That's why we call it a lucky guess, right? Yeah. So the question is, how do we make the guess, right? How do we make the guess? So your guess is not random, it's not wild. You need to follow a certain rule here, right? So that rule is given in the table, okay, as in the handout here. So let me open the table here. Yeah. Anybody have a handout here? No, who doesn't have a handout? Yeah, go ahead. Okay, so I said it's not wild guess. So how do we make the guess then? Here is how you make this guess. Suppose this column here, okay, is what f of t, the input f of t looks like. Basically, what the other side, the right side of this second order ODE looks like. So first one looks like exponential function. Second one is basically t to the power something, and this is something like a sine or cosine, or maybe a combination of sine cosine, or maybe it's a combination exponential and sine cosine together, right? Okay. Then your first step, okay, your first step for the YP, your guess, is exactly the same format. Okay. So this is what it means here. Let's say if f of t equal to e to the power of at, it doesn't matter what this value here is, then your guess will be c e to the power of at. So c is what you need to find out. A is the same number as this a at here. Okay? Yeah. Second one here, let's say you have a f of t maybe equal to t squared, for example. Okay? T squared. Then your yp of t, your guess, is not just a t squared. It's going to be t squared, a number, t, and 1. Okay, so you had to cover the three terms there. Okay. If f of t is a cosine or sine, right, or combination of sine, cosine, it doesn't matter. and your yp of t all have the same kind of a gas. So it's a number n, number m, which are constant that you're going to have to find it out, multiplied by a cosine and sine with the same frequency omega here. All right? Yeah. If it's a combination of this one here, then you have also a combination of a gas set here. Okay, so that's basically what happens. Now you look at the last one here, right? Look at the last one here. So when you have a ke to the power of at, your gas is ce to the power of at, right? Now here is ke to the power of alpha t, cosine and sine here. But look at this one here. I don't have any k here anymore, right? I don't have any c here. Like that, I have a c here, right? But this one here, I don't have the c here. There's a reason here, actually. You don't really have to have the c there. Why is that? Let's say you put a c here, then what happened? Exactly. Yeah. So that's the reason you don't need the c over here anymore, right? Yeah. If you put a c here, and chances are you're still going to be able to get the same results because you're going to multiply c into it, right? Yeah. So this is the table you're going to follow, right? Yeah. I think you will have this one in the final exam, this formula here. But at this stage, when you do your assignments, okay, and I need you to get familiar with how many cases? 1, 2, 3, 4. So 4 different cases essentially, right? Yeah, so not bad. Okay, so that solved the problem here. So your guess. So you guess based on this table, which is that the table. I don't have a number for this table, right? Yeah, in lecture notes. Okay, yeah. So that's the guess. If you look at on the other side of your page, okay, look on the other side of the page. I have more complicated cases. Okay, more complicated cases here. So more complicated, basically, it's just a combination of the simple cases, right? So for example, you look at this. If you look at this. If you look at, let's say this one here, 5t squared plus 2t minus 3. So it appears there are 3 things here, right? 3 things here. But actually, the first one is the dominant one because the other 2 is sort of a special case here. So when you guess, you're actually just base your guess based on this 5t squared, 5t cubed here. Okay. Here is a combination. Here's a combination of t squared e terms. So there's a combination. Your guess is also going to be a combination of these 2. Okay, yeah. Phi cosine, that's not a combination. Here's a 60 squared sine. That's a combination, right? It's a combination here. So this is a little bit more complicated because you got a sine here. If I don't have any sine, my guess is going to be, if I don't have a 60 squared, if I don't have this term here, my guess will be just n cosine omega t plus m sine omega t, right? Now because this guy here, instead of using the n and m, so you replace the n and m with the corresponding guess for the 60 squared, right? But however, there's different constants here, right? So this kind of case is probably going to take a while to solve for A, B, C, and D, E, F. Okay, yeah, but it doesn't matter. So you need to basically always focus on is where do I get the guess? Your guess is based on the preliminary table over here. If there's a combination of these 2 here, okay, you go to the second table. Okay, yeah. Okay, so that solved the gas problem here now. Okay, however, there are a couple of rules you have to also still to follow. This first one here, the gas, I will call it basic rule here. Okay, so the first one here, running out of space here. Okay. Didn't work. So call it basic rule. Okay. First one, I call it basic rule here. However, okay, you do have a couple of different situations here. So the second one here I would call it modification rule. Okay, so modifications. So modification rule here is this. Now suppose that, okay, your YP, so you guess your YP based on first rule, right? You guess your YP based on first rule. But then you find that, so YP is the same as, okay, it's the same as the basis solution of homogeneous ODE. Okay, the homogeneous ODE here. So what does that mean? See, here is your homogeneous one, right? Here is A y double prime. So y1 and y2, they are a y double prime plus b y prime plus c y equal to 0. So y1 and y2 are the so-called basis solution of this one here, right? And you form your general solution by c1 y1 plus c1 y c2 y2. So y1 y2 are the basis solution of this one here. Now if it happened that this yp, your first guess from the first basic rule, happened to be the same as maybe as y1 or maybe as y2, right? Then that's where we need to apply this modification rule right here. All right? Yeah, this modification. So here's the idea here, right? You see, my general solution for this one here is what? C1 y1 plus C2 y2 plus yp, right? Plus yp. Now, if yp is the same as one of this, so let's say maybe this is e to the power of negative t, for example, right? And your yp, your guess is also maybe c e to the power of yp, but this is different. So you look at this one here, they're the same thing, right? They're the same thing. They're linear what? Linear dependent, right? Linear dependent. So if they're linear dependent, why do I need this yp here? It's already here, right? So it doesn't make any sense to have another similar term here. This is why we need to make a modification here. So then how do we make the modification then? The modification, the idea is to make this lucky guess to be different from this, whatever the similar term over there, right? Yeah. So what do we do is, right? So the first thing is, if this is the same as the basis here, then there are two different cases, right? What you do is you multiply by t, okay? By t with initial guess. Okay, you multiply by t when yp, your initial guess, only the same as one of them. So when yp is the same as y1 or, okay, it's or y2. Okay. So basically, yp only repeat once of what this basis y1, y2 there. All right. So you multiply by t. Is that good? Yeah. So in this particular case, okay, actually this y1 is not the same as y2. All right. Yeah. But there are three different cases for y1 and y2. The second case is when y1 and 2 are double roots repeated, right? So basically, in that particular case, if y1 equal to y2, so you have a double roots, and initial yp equal to y1, not equal, the same as y1, okay? In same form as y1, okay, in same form. Then in this case here, your yp or the modification to your initial gas, you multiply by what? T squared. Okay, so just basically keep multiplying another t. So then multiply initial gas by t squared. Okay, t squared. So now you can imagine if there are high order differential equation, then you might have a roots repeated by maybe n number of times, right? Yeah, who knows? And in that particular case, your highest chance is multiplying so t squared maybe by t to the power of n. Yeah, so we're not going to come to that anyway. So restrict to this two different cases here. Okay, so we'll look at examples later, but just a summary. So that's modification rule here. Okay, modification rule. And the last rule, I think we use C here. The last rule is called sum rule. Okay, sum rule. So for this sum rule here, it's actually quite simple. Essentially, f of t, okay, is an addition of different basic form, okay, from the table. So maybe f of t is addition of a sine plus an exponential, and maybe f of t is a t squared plus a sine, right? So that's f of t. What will f of t look like? Then when you take your initial gas, okay, your initial gas is basically also a summation of the initial gas. That's what it means here. Okay, so initial gas, okay, is also an addition. Okay, it's also an addition format. Okay, all right. So I guess, just talking here doesn't make much sense. Maybe, let's look at the. We're not going to solve anything, but just look at a couple of differential equations here, right? Yeah, just look at a couple of differential equations. Okay, so for example, let's say I'll just talk about the summation rule here. Maybe let's say if f of t equal to t squared plus 4t. Okay, e to the power 3t plus 5 cosine 2t, right? So let's say this is f of t here. And what would be the initial gas? Okay, so what would be the initial gas now? So look at basically, in this case here, we apply the summation rule here. So if you look at your table, how many different types? This is one type here, right? And this is a multiplication of two types. And this is a one type, sine cosine. Okay. So for t squared, what will be your lucky guess? That's right. Okay, this is the t squared gas. Don't forget to write down everything here, right, until the k naught. And for this 4t e to the power 3t, now that's a tricky one there, right? So there are two things here. T e to the 3t. If it's just a e to the 3t, it will be just c e to the power 3t, right? But you have this t at here. So in terms of c at here, so we're gonna use what? So here's already key 1, key naught now. So you cannot use key 1, key naught anymore. So let's use a ct plus d maybe. Right? See, this ct plus d is the corresponding gas for the t. And the e to the power 3t is the gas for that. You don't need to multiply another constant anymore, right? Because you already have c and d here. So that's the second gas for this one here. And the last one is 5 that, so that's just one sine cosine here. So it's going to be n cosine 2t plus m sine 2t, right? Yeah. Okay, so now when it comes to solving, right? This is your lucky guess, right? But when it comes to actual solving this one here, what I would recommend is doing this. You consider this is your yp1, yp2, and yp3. Okay, so you consider you have 3 different gases there. Okay, 3 different gases. Then you're gonna basically try to solve each one of these constants here, right? Separately. Okay, separately, not a whole bunch of these things all together. Because as you're gonna see is, our objective is to figure out what are the constants here. In a particular solution, you cannot keep a general constant in it. You have to solve for the constants, right? Yeah. So how do I figure out the constant values? Then what do we do? Because we said this is a particular solution, right? So which means this yp satisfy our non-homogeneous equation. So we're going to have to substitute this yp prime and the yp double prime back into the given differential equations in order to solve for the constants. So look at this one here, right? If let's say you have a case of this, and then you're gonna take a yp prime, yp double prime, and then substitute everything back into original one here, right? So you're gonna need maybe a 10 by 11 size of papers to write everything out, right? So essentially, in this case, if this is the case here, chances are a good way of practice is to separate them. Okay, separate them. All right, so let's take a look at well, we don't have time anymore. Okay, well, we'll take a look at examples in the next lecture.